Hello everyone. Today we will see the different types of damping. There are three different kinds of damping. They are referred to as overdamped, underdamped and critically damped systems. So in the case of damping, we have already set up the equations for a differential equation for damped harmonic oscillator. So we will solve those equation. We'll try to solve those equation, and when we solve that equation, we will arrive at a point where there will be certain constants appearing in the system. So depending on the relative values of some constants, we will have three different cases which we call overdamping, underdamping and critical damping. So this is the differential equation that we have set up earlier to describe a system which is experiencing damping. The differential equation d square x by dt square plus 2k dx by dt plus omega 0 square x equal to 0. This stands for the differential equation for a damped harmonic oscillator. So the constants which are appearing in this equation, k is the damping constant and omega 0 is the natural frequency. So these constants, I would like to remind you once more. The damping constant k is related to the damping coefficient gamma through this equation. Gamma by m is equal to 2k, and it is also equal to 1 by tau, where tau is the time constant for damping. And another quantity or parameter which is characteristic of this system which is undergoing damped harmonic oscillation is this natural frequency omega 0, which is related to the spring constant capital K. Through this equation, omega 0 square is equal to k by m, where m is the mass of the body which is executing the oscillation. So we will look at this equation. So in order to understand what is overdamping, underdamping and critical damping, we will have to try to solve this equation and see the different cases with respect to the values of damping constant k and natural frequency omega 0. So we will see that first of all we will try to solve that equation. So in order to solve that equation, what we do is, so this is a second order differential equation. We will assume a solution of this form. X is the displacement. So this second order differential equation stands for the displacement of the body which is undergoing a simple harmonic motion in the presence of damping. So in order to solve that, we will assume this form of a solution. Solve means you'll have to find out what is x, or you'll have to get an equation which can represent x, which is the displacement as a function of time. So we will assume a solution of this form. X is equal to a e raised to alpha t. In this case, a is a constant, alpha is a constant. So the procedure is to find out using this expression for x, which is given in this equation number 2. We will use this expression for x and we will substitute it in equation number 1, and we will have to obtain the constants a and alpha. So you can see, first of all, what we have to do is, in the second order differential equation we have got d square x by dt square and dx by dt. Dx by dt is the first order derivative of x, and d square x by dt square is the second order derivative with respect to time. So let me write down the first order differential as x dot and second order differential as x double dot. So from this equation, x is equal to a e raised to alpha t. You'll have to first of all find out dx by dt x dot, which will be alpha a e raised to alpha t. Then x double dot, which is d square x by dt square, x double dot, that you can easily obtain as alpha square a e raised to alpha t. So what we do is we will use this value of dx by dt and d square x by dt square. We'll put it in this equation 1. So we will be getting alpha square a e raised to alpha t plus 2k alpha a e raised to alpha t plus omega 0 square a e raised to alpha t equal to 0. I have written these common terms which are common parameter which is appearing in all these three terms, which is a e raised to alpha t. That is common. So since the right hand side is 0, you can delete these common terms and you will be left with alpha square plus 2k alpha plus omega 0 square equal to 0. So that is what is written here. Alpha square plus 2k alpha plus omega 0 square equal to 0. So if you look at this equation, you can see that it is a quadratic equation in alpha of the form ax square plus bx plus c equal to 0. So this equation is similar to this equation. It is a quadratic equation in alpha, which means it is very easy to solve this equation to find out alpha. What we do is, if you have got an equation of this form ax square plus bx plus c equal to 0, we know that the solution is minus b plus or minus root of b square minus 4ac divided by 2a. So we will just apply that in this equation and we will find out alpha. Here a alpha square, so that means a is equal to 1, ax square plus bx, so b is 2k, plus c is omega 0 square. So that is what we are doing here. That gives you alpha as minus 2k plus or minus root of b square, b we have got 2k, minus 4ac, a is 1, c is omega 0 square, divided by 2a, a is 1. So we will just cancel. For example, we have got a square root here, and we have got, this will come out to be 4k square, and here we have got 4 omega 0 square. So we can take out the 4 outside. When it comes out of the square root, it will become 2. So we'll cancel all the 2 from all this term, and the term in the denominator we will cancel, and we will be getting an equation for alpha as minus k plus or minus root of k square minus omega 0 square, where k is the damping constant and omega 0 is the natural frequency. Natural frequency means it is the frequency with which it would have oscillated in the absence of damping. Now what we do is, so in this equation 2b, we have got a square root symbol, and there are two terms in the square root symbol, k square minus omega 0 square. So depending on the relative values of k and omega 0, we can have, for example, if k is equal to omega 0, the square root term will disappear. If k is more than omega 0, we will be having a square root of a positive quantity, and if k is less than omega 0, we will be having square root of a negative quantity. So when you have got square root of a negative quantity, that will become imaginary. So actually these are the three different instances that we have to consider in order to see the conditions under which we will be getting critical damping, over damping, and under damping. So let me write down that equation for x, which we have assumed earlier. Once more, x is equal to a e raised to alpha t, and we have obtained right now alpha as minus k plus or minus root of k square minus omega 0 square. So as I told you, we have got alpha. Right now we have, actually what we have to do is we will have to find out capital A and alpha. Right now what we have done is we have obtained alpha in terms of the constants that will govern the oscillation, which is damping constant and natural frequency of oscillation. So what we do is we have got two possibilities for alpha, which is minus k plus root of k square minus omega 0 square, and minus k minus root of k square minus omega 0 square. So that should be applied here, which means when you consider both possibilities of alpha, the most general expression for x is going to be a linear combination of the results which we will get when you put the two different values of alpha. So that is what is written here. X is equal to some constant into e raised to minus k plus root of k square minus omega 0 square into t, plus another constant into e raised to minus k minus root of k square minus omega 0 square into t. So this is one alpha, one possible, that is actually one possible root of the quadratic equation that we have earlier set up in alpha, and this is the second root of that quadratic equation. So that means alpha has got two possibilities, or there are two possible solutions to alpha, and when considering both these possibilities, we get the most general expression for x as given by this equation 3. Now depending on the value of k and omega 0, you can see as I explained right now, if k is equal to omega 0, then the square root term will disappear. So let us see, let us consider these three cases one by one. So this is the equation for x. X is the displacement of the body which is executing oscillation in the presence of damping. And in order to identify the three different possible types of damping, we will consider all possible values of relative values of k and omega 0, k and omega 0. So for example, when k is less than omega 0, k is greater than omega 0, and k is equal to omega 0. These are the three possibilities. For example, when k is equal to omega 0, this is referred to as critically damped oscillator. When k is equal to omega 0, this is called it is referred to as critical damping. And when k is more, damping constant, when it is more than the natural frequency of oscillation, that is referred to as overdamping. And when k is less than omega 0, it is referred to as underdamping. So we will just have a look at, we have to actually look at the solution of these three cases in detail. But right now we can have a quick look at the equation and see how it will look like. For example, how x is going to behave in these three cases we will see. For example, first of all, let us see k equal to 0. When k equal to 0, this term root of k square minus omega 0 square will disappear from both these terms. So what we will be having is some constant into e raised to minus kt plus another constant into e raised to minus kt. So essentially what we are going to get is a1 plus a2 into e raised to minus kt. So when, because of the presence of the term like e raised to minus kt, it means it is going to exponentially decrease. So that means we start with an oscillator, we call it a simple harmonic oscillator, and then it is experiencing damping. But depending on the value of the damping constant in omega 0, for example, when k is equal to omega 0, that is a special case which we call critical damping. In that case, what we have seen is x, or the displacement, the expression for displacement will be like a1 plus a2 into e raised to minus kt. So that means a1 and a2 are some kind of an amplitude factor. We'll have to actually find out exact form of this a1 and a2, for which we will have to look at the solution in detail. But even without looking into the equation in detail, we will have an idea about how this displacement is going to behave in the presence of critical damping. Since it is a1 plus a2, these are some kind of amplitude factors. Okay, let us take it to be amplitude factor. But we have got an exponential factor e raised to minus kt, which means as a function of time, the amplitude is going to decrease exponentially. So that is critical damping. And in the case of over damping, when k is more than omega 0, what we are having is when k is more than omega 0, the square root is positive. So here also this is positive, this is positive. So when you look at this equation again, what we are having is a1 e raised to minus k plus a positive quantity into t plus a2 e raised to minus k minus a positive quantity into t. So when you look at, because of the presence of this minus k here, what is going to happen is when you look at these possibilities, minus k plus a positive quantity which is k square root of k square minus omega 0 square. So since we have got the condition that k is more than omega 0, what we have is, because of the presence of this negative k here, negative k plus a positive quantity, negative k minus a positive quantity. So essentially what we are going to have is this will also be exponential, the exponential term in both these exponential term, or the argument of this exponent in both these terms will be negative. So that means in the case of over damping, where k is more than omega 0, in the case of over damping also, we will see that x will decrease exponentially with time. but the way in which it is decreasing exponentially with time, actually in case of overdamping and critical damping, in both these cases amplitude will decrease exponentially with time. But when you compare overdamping and underdamping, as I told you, as I mentioned earlier, we have to actually look at this nature of A1 and A2 to clearly understand how this is going to behave. But in general, we can say both these will be exponentially decreasing with time, or the amplitude will exponentially decrease with time. But in the case of critical damping, the system will come to equilibrium faster than in the case of overdamping. And the third possibility is underdamping. Underdamping means k is less than omega 0. So when k is less than omega 0, what is going to happen is that this quantity within the square root is negative. So you will be having, for example, you can write it like negative of omega 0 square minus k square, and you take the negative outside the square root, you will be having I. So that means that term is going to be imaginary, or you'll be having a term like e raised to I some constant, let us say omega 0 square minus k square. We can define it to be a new frequency omega. So we'll be having a term like e raised to I omega t. Okay, that omega can be considered to be the new frequency with which the system is going to oscillate. And you know that e raised to I omega t can be written as cos omega t plus I sin omega t, which means that will represent sinusoidal oscillations. Okay, or e raised to I theta is the complex exponential, which stands for oscillation, sinusoidal oscillation. So that means in the case of underdamping, or when k is less than omega 0, the system will be oscillating because of the presence of e raised to I theta term, or e raised to I omega 0 square minus k square t. Why I am saying omega 0 square minus k square is because omega 0 is more than k, so I just write it as minus of when k square is less than omega 0, I can write it as negative of omega 0 square minus k square. And so the negative I will take outside the square root sign, and it will become I. And then what is left behind inside the square root is omega 0 square minus k square, which means that is the new frequency, or that decides the new frequency. Root of omega 0 square minus k square can be considered to be a new frequency. So that means if omega 0 is the natural frequency, then the new frequency will be omega 0 square minus k square, which will be smaller than the natural frequency. So the effects of damping you can see from this example. So in the case of underdamping, or when the damping is small, the system will be oscillating, but it will be oscillating with a frequency smaller than the natural frequency. Then another effect that you have already seen is it will be oscillating, but its amplitude will keep on decreasing. So these are the two main effects of damping. The amplitude will, in the case of small damping, let us say, the effects of damping can be specified as uh, oscillation frequency will decrease compared to its natural frequency, and the system will be oscillating with a constantly decreasing amplitude. So when you consider these three examples, that we can actually graphically represent them in different ways. Like this, for example, we have got overdamping. Overdamping, there is no oscillation, but the amplitude will the system will come to equilibrium, which is the mean position, which is represented over here. It will come to equilibrium. In the case of critical damping also, there is no oscillation. The amplitude will be exponentially decreasing, and it will come to equilibrium. But when you compare overdamping and critical damping, overdamping will take a longer time to settle. It will take longer time to come to the equilibrium position, whereas in the case of critical damping, it will be coming faster to the equilibrium position. And in both these cases, there is no oscillation. Whereas in the case of underdamping, or when the damping is low, the system will oscillate. But it will be oscillating with a frequency smaller than its natural frequency. Or in the event of no damping, what could be the frequency with which it would have oscillated? Now it will be oscillating with a frequency smaller than the natural frequency, because the new frequency you can relate it to the original frequency as new frequency is equal to omega 0 square minus k square whole raised to half. So these three examples illustrate the comparison between overdamping, underdamping and critical damping. So now we will see the applications of some daily life applications, or some applications that you can find in physics lab. Most important application is for critical damping as far as a physicist is concerned, or when you come to the physics lab you can see some instruments which are working based on critical damping. For example, let us now compare these different cases. On the leftmost side you can see a system which is oscillating when there is no damping at all. So this is undamped case. Whereas when there is small damping, or when there is a situation which we call underdamping, it will oscillate, but its amplitude will it will settle. Its amplitude oscillation will die out slowly, and this is referred to as underdamping. When the damping is small, there is a constant reduction in amplitude. There will be oscillation, but there will be constant reduction in amplitude, and the system will come to a stop. So this is one simple example that you can say is, for example, a swing. When it is swinging, it will actually, if you don't keep on pushing, it will oscillation will die out, it will come to a stop. And the damping is provided by the resistance due to air. And on the rightmost side you can see the two cases of overdamping and critical damping, where in both these cases there are no oscillations. The damping, because in the solution for x, we have seen that it consists of exponentially decreasing terms, whereas in the case of critical damping, the system will come to equilibrium position sooner compared to the overdamping case. And where can we use critical dampings? This is an example of shock absorbers which are used in vehicles. So in the case of a shock absorber, there will be an oil which is used to provide damping effect to the body, which is with damping effect, so that the vibrations will be dying out. So in this case, what we require is when there is vibration, it should be minimized. So whether we require overdamping, underdamping or critical damping, when we think about that, obviously we don't want underdamping, because underdamping means oscillations will continue and it will be dying out slowly. Then the choices that are left behind is overdamping and critical damping. So when if you recall the equations for or the condition for critical damping and overdamping, we have seen that in the case of overdamping, the displacement of the body which has taken place from the equilibrium position, that body will come back to the equilibrium position in the case of overdamping, but it will be taking longer time to do that, whereas in the case of critical damping, it will be coming to the equilibrium faster. So what we need in this situation is we'll have to cancel the vibrations as fast as possible. So in this case, what is happening is the system will be designed in such a way that the critical damping will be taking place, and the vibrations will be, or the disturbance which has taken place will be cancelled as quickly as possible. So here also the same thing is explained. What you have to imagine is it is not overdamping which should happen here, because in the case of overdamping, the system will be taking a longer time to settle. So instead of overdamping, it is critical damping which is required in the case of shock absorbers. Now this is a familiar example for you. This is galvanometer. You have seen galvanometer in the case of the experiment that you have done using a potentiometer. So in the case of potentiometer, when you press the jockey at the point A and point B, you can see deflection in the galvanometer. So when you press it A, it will be deflecting to one side, and when you are pressing it at B, the deflection will be in the opposite direction, which means in these two cases the currents will be flowing in opposite directions. So this is a type of device which gives you a deflection, and that deflection is can be read in terms of the magnitude of the current. So when there is no current, the needle should be coming back to the equilibrium position. So this is a system in which when there is so the deflection of the needle is a disturbance from the equilibrium position, which is due to the current which is flowing. And when current is zero, there will be a spring in the system which will bring this needle back to the equilibrium position to indicate that current is zero. So in that case also, what we have to imagine is that when you release the jockey, the needle will be coming back to the equilibrium position. It doesn't go to the other side. Okay, that means there is no oscillation, but when the jockey is released, the spring will bring the needle back to the equilibrium position, and it doesn't allow this needle to go to the other side. So that happens very quickly. So this is also an example for system that you can see in physics lab, which exhibits critical damping. So here I have listed out some of the comparisons of underdamped and overdamped case. So underdamping, in the case of underdamping, if you recall the equations that stand for x, which is displacement of the body, you will see that there will be both exponentially decreasing term and uh, a, a, a sinusoidal term. So that means there will be oscillation, but depending on the strength of damping, the oscillations will be there. Generally, this is happening in the case of low damping. So oscillation will be there because of the presence of e raised to I omega t term. But in addition to that, there is e raised to minus kt term also, which is an exponentially decreasing term. So sinusoidal term will result in oscillation, and exponentially decreasing term will result in exponential decrease in amplitude. So oscillations will be there, but it will be dying out slowly. So that is underdamped case, and this is a very familiar example of swing, which is swinging in air because of air resistance. Oscillations will be there, but it will die out slowly. And over damping, on the other hand, it is heavy damping. There will not be any oscillation, and the body which has been displaced from the equilibrium, it will come back to the equilibrium position, but it will take some time compared to the critical damping case. Both in the case of critical damping and over damping, there will not be any oscillation, but the body will be coming back to the equilibrium position. But in the case of over damping, it will take more time to come to the equilibrium position than it would have taken in the case of critical damping. So I will conclude by saying the effects of small damping, which means under damping. If there is under damping, the oscillations will continue, but the oscillation frequency will be equal to, as I explained earlier, the oscillation frequency. The oscillation frequency can be taken from the sinusoidal term. For example, if you have got a term like sine omega t, then omega will be the oscillation frequency. Or if you have got a term like e raised to I omega t, that omega will be the oscillation frequency. So I showed you earlier that in the case of small damping, when k square is less than omega 0 square, we can rewrite it as that amplitude, I mean the exponent factor or the frequency factor which is appearing in the exponent as omega 0 square minus k square, and that means the new frequency will be smaller than the natural frequency. Natural frequency is omega 0 square, natural frequency is omega 0. New frequency will come out to be root of omega 0 square minus k square, which is obviously smaller than omega 0. That means in the event of small damping, oscillation will be there, but the oscillation will die out. The amplitude of the oscillation will die out because of the presence of the exponentially decreasing term in the equation for x. And in addition to that, it will be oscillating with a new frequency which is different from the natural frequency, which is different, and it is smaller than the natural frequency. So these are the two important effects of small damping. So in the next class we will see the last topic, which is forced oscillation, and in that context we'll also discuss a phenomenon which we call resonance.